Yeah, welcome back again. In this lecture, we are going to be looking at the communication interface for embedded systems. Communication interface. Okay, we start with um, what the communication interface is. So we say communication interface as the point, the channel through which the subsystems of the the subsystems of the embedded system communicate within the board level or outside of the board itself. So it's actually very necessary for communicating the interface. Every communication interface in it is very necessary for the subsystems of the embedded system to communicate with each other, with the system itself, and then with the external world. And we can view this thing in two different perspectives. So one is onboard communication interface, or what we call the board level communication. And examples of such communications are the I2C communication interface, SPI, rep preference interface, UART, one wire, and parallel bus interface. And then we have the external or product level communication interface. Okay, examples of the wireless examples of them are the wireless interfaces, the infrared, the Bluetooth, wireless LAN or Wi-Fi, radio frequency, GPRS. Okay, examples of wired interfaces in the product level communication interface are the RS232C and RS422 and RS485 interfaces. And then we'll have the Ethernet interfaces, the Ethernet TCP/IP interface, and the IEEE 1394 port and parallel ports that are available. Okay, so next we talk about the inter-integrated circuit bus, which is called the I2C bus. All right. So when you look at the I2C bus, you'll find the SDA and then you have the SCL. So, and upon those two lines, the SDA is the serial data line and this is the serial clock line. Okay, and we have many devices there that are connected to both of those interfaces. So each of them is connected to the serial data and the serial clock. Here we have the serial data, we have the serial clock, the serial data, we have the serial clock, and all of them are connected to the VCC through a pull-up resistor. Okay, R1 and the R2. All right. Okay. So, sorry, I'm coming. Okay. So both of them are connected to through a pull-up resistor. All right. So the inter-integrated circuit bus is actually a synchronous bidirectional half-duplex two-wire serial interface bus. It's actually a two-wire interface bus. Okay, I'm coming. Okay, so the concept of the I2C bus was developed by Philips Semiconductor in early 1980s, and the original intention of the I2C was to provide an easy way of connection between the microprocessor, microcontroller system, and the peripheral chips in television sets. Okay, so it is comprised of the serial clock and the serial data lines. The serial clock on its own is responsible for generating synchronization clock pulses, and the serial data is responsible for transmitting the serial data across devices. So I2 bus is a shared bus system to which many number of I2 devices, I2C devices can be connected. Alright, so devices connected to the I2C bus can act either as a master or as a slave. When they act as a master, they will be responsible for controlling the communication by initiating or terminating the data transfer, right? Sending and generating necessary synchronization pulses for data transfer. So during this the transfer of data, at that point the slave device will wait for a command from the master device and then respond upon receiving the command. In other words, it's a kind of, when the master device wants to send something to the slave device, it will knock at the door, and then the slave device will wait for that command, and when he receives the knock, he will respond by telling the master, I'm available to receive the command, right? So the master and slave devices can act either as a transmitter or as a receiver. So regardless of whether a master is acting as a transmitter or as a receiver, the synchronization pulse is actually generated by the master device only, right? So an I2C communication supports multi-masters on the same bus. Okay, so next we look at how this data is transferred. Okay, so we look at the sequence of operation for communicating with an I2C slave device. All right, so during communication, the master device will pull the clock line of the bus, okay, the clock line of the bus to a high, and then the master device also will pull the data line to a low. And when the serial clock line is at logic 1 and the serial data line at the logic 0, this particular point will indicate the start of data transfer. So when you look at this diagram now, you will notice that at this particular point, when this is at logic 1 and that one, this is logic 1 here, and this place now is logic 0, the same here, this is logic 0. So when it pulls this point to logic 1 and this one to logic 0, that is the serial data, when it pulls this, it is the start condition for data transfer. Now during that time, the master first of all sends the 7-bit or 10-bit wide of the slave device, the address to the slave device. It sends an address to the slave device, alright? So, but it is the device which it wants to communicate, right? The clock pulses are generated at this at the clock line for synchronizing. So for synchronizing the bit reception by the slave. In other words, he sends it now, trying to make it in sequence so that I send a clock signal around it so that this thing will flow in sequence until the intended device receives it. Okay, so the most significant bit of the data is always the first to be transmitted, and it's always the first to be transmitted. Along that part, the data in the bus is valid during the high period of the clock signal. So the data is only valid when the clock signal is at high level. Alright. So in normal data transfers, the data line only changes state when the clock is low. The master waits for the acknowledgement when it has sent the 7 to or 10 bit 8 so 10 or 10 bit wide signal or message to the slave. He will wait for the acknowledgement bit from the slave device whose address is sent on the bus. Along with, when he sends that address, he sends it along with the read or write operation command. So note that when the master writes to the slave, know that the master writes only to the slave when the data signal is 0, and he will read from it when the data signal is 1. Okay, so the slave device that is connected to the bus now compares the slave device is not just one. All the slave devices, when they see the address in the bus, what they do is to compare the address with the address that was assigned onto them. All right. So the slave device with the address requested by the master device respond by sending an acknowledgement bit, that is bit value 1, over the SDA line. In other words, the moment the slave device that has that information sees it, you recognize it. Oh, it is me they are calling. Okay, so it now sends a bit value 1 to the master to tell the master, okay, I'm here. So upon receiving the acknowledgement bit, the master will now send the 8-bit data to the slave device over the SDA line. So if the requested operation is right, that is when the master sends that 8-bit. And if the requested operation is is read from the device, now the master will wait and the slave device will send the data to the master, because it is a read operation from the master, but actually it is a sending or a write. So when it's a read operation from the side of the master, it becomes a write operation from the side of the slave. All right. Okay. So the master will now wait for the acknowledgement bit from the device upon byte transfer complete for a write operation. All right. So when the master finishes writing to the device, it will now wait for the device to say, okay, you are done writing. Okay, for the write operation, and then sends an acknowledged bit to the slave device for a read operation. In other words, he receives an acknowledgement bit from the one it writes to, and then it sends to the one that wrote to it. All right. Okay. So the master now will terminate the data transfer by pulling the SDA line and the clock line to a high position, both of them. So when you look at the end of this now, you will discover that this is actually 0, this is actually 1, this is actually 0, this is actually 1. So for the data transfer to end, the master will pull this place to high and then this one to high. So at this point in time now, where the data transfer will stop. All right. So that is the operation for communicating with an I2C slave device. All right. Okay. Next, we look at the serial peripheral interface. Okay. Now, when you look at the serial peripheral interface, you discover that we have only one master and then many slaves. And then we basically have 4 communication lines entering each slave. First one is the clock, second one is the serial data in, and the third one is the serial data out, that is from the slave, and then the fourth one is actually selecting of register. Okay, selecting of the slave device. Alright. Okay, so the SPI is a synchronous bidirectional full duplex wire serial interface bus. Alright, full duplex 4-wire serial interface bus. SPI is a single master multi-slave system. It has only one master. All right, so it only has one master, and then it can have n slave system, n slaves. Okay, slave 1, 2, 3, and so on to n. All right, so that is it. It's a single master multi-slave system. So there is also the possibility of having more than one master, provided that only one master device is active at any given time. Okay, it is used to send data between microcontrollers and the small peripheral devices like registers, sensors, and SD cards, as the case may be. So SPI requires 4 signal lines for communication, which are the master out, slave in. You have the OR, you call it the slave in or slave data in. You have the master in, slave out, or you call it SDO or SO. All right. Then we'll have the clock signal. All right. And then we have the select, slave select. Okay. So that is the 4 basic signals that we have there. Okay, next we look at the data flow in SPI bus. All right. So from the figure that we are considering now, all right, you will discover that the shift registers in master and slave devices are connected together, all right, such that it forms a loop. So when you look at this place, you see the movement of the arrow from this particular register to this particular register, all right, and it moves this way and moves this way, all right, and then gets back to the beginning of the master register in the master device. Okay, so it forms a loop. These registers operate in a serial in, serial out. In other words, it moves step by step from all these points. It will move. Okay, A7 will move at every clock cycle. It will move this way, and so on and so forth. So it will continue to move, and the same thing with the values inside of all of these boxes. It will continue to move in a sequence that way. Okay, the output of a register is connected to the input of the other register, and the clock signal is generated by the master device, which controls the flow of data. So what makes the master is that the control is there. It is the one in charge of the control. It's the one in charge of the control of data flow from this place, from the master itself to the slave. All right. So in the buffer register, okay, I said that the clock signal is generated by the master and it controls that. Okay. Then in the diagram, the buffer register is actually omitted. So if we need to transmit data, we need to write to the buffer first. We need to write to the buffer register first, and then it will automatically be written to the shift register when it is free, and the transmission will start. So basically, we are supposed to be having something like this. We have this too. We have our buffer like this, and then this will come to a buffer again before it comes to this device. All right. Okay, so that is it. So next we look at one wire interface protocol. Okay, so when you look at it, we say that one wire is a device communication bus system that's designed by Dallas Corporation. All right, with low speed. It has low speed data and signaling and power over a conductor. So it is actually typically for low data rates and longer range. So it's typically used to communicate with more inexpensive devices such as digital thermometers. Now, one distinctive feature of the bus is the possibility of using only two wires, which you can see in this particular diagram. So you have this, I'll call it positive line, and then we'll have this one. So the data line is actually connected to the VCC, so a pull-up resistor, and then you will have the ground. Okay, so to accomplish this one-wire device, to accomplish the communication here, is that the one-wire device will include an 800 picofarad capacitor to actually store charge and to power the device during the periods when the data line is active. There's always one master in overall charge, which may be a PC or a microcontroller. Okay, so the advantages of this device is that many devices can share the same bus or have many devices. As you can see, we'll have one master here, and then we have the bus line going here, and then we'll have slave number 1, slave number 2, slave number 3, and it continues that way. Okay, so we can as well have slave number 4, right, slave number 4, and so on and so forth. Okay, each device on the bus has a genuine 64-bit serial number. So during communication, the least significant byte of the serial number is an 8-bit number that tells the type of the device. Okay, now the most significant byte is actually a standard 8-bit CRC, cyclic redundancy check, for errors. So the master usually starts the transmission with a reset pulse, which pulls the wire to 0 volts. Now, when the reset pulse comes, it pulls the wire to a point of 0 volts for about 480 microseconds, and this resets every slave device on the bus. So after that, any slave device, if present, will now show that it exists with a presence pulse. All right, so it's at a point, it's just like saying who are here. All right, it activates them, and those that are there will actually show that they are there with a presence pulse, and that presence pulse, it holds the pulse low for at least, all right, 60 seconds after the 60 microseconds after the master releases the bus. All right, now to send a 1, the bus master sends a very brief 1 to 15 microsecond low pulse. All right, to send a high, the master will send a 60 micro low pulse. Right, so the difference here is not the pulse itself. The difference here is the duration of a pulse. All right, so when receiving data, the master starts by sending 1 to 15 microsecond 0 volt pulse to the slave unit. All right, and then if the transmitting slave unit wants to send a high, it does nothing, and the pulse goes to a pulled up voltage. Okay, so if a slave really wants to send something, it wouldn't indicate anything, so it does nothing, and then giving the master a signal that he wants to actually send something. So if the transmitting slave wants to send a 0, it pulls the data line to ground for 60 microseconds, and that is the way the communication goes from master to slave in the one wire interface. Okay, so at this point I think we are going to end this particular lecture. Next we are going to start at product level communication interface. Okay, see you again in another lecture.